Welcome to Elementary Real Analysis. Today we are going to explore one of the most beautiful and intuitive concepts in mathematics, known as the Monotone Convergence Theorem. If you have ever wondered how we can be absolutely sure that a sequence of numbers settles down to a final value without blowing up to infinity, this theorem is the answer. It is a foundational tool that you will use throughout your mathematical journey. Let us dive right in and build our understanding from the ground up. To understand this theorem, imagine you're climbing a staircase inside a room. Every step you take moves you higher up, and you never step down. In mathematics, a list of numbers that only goes up is called a monotone increasing sequence. Now, imagine this room has a solid ceiling. The ceiling acts as an upper limit that you absolutely cannot break through. If you keep taking steps upward but you can never pass the ceiling, what has to happen? You must eventually level off and get closer and closer to some specific height. Now that we have a physical intuition, let us define the exact mathematical terms. A sequence is simply an ordered list of numbers. We say a sequence is monotone if it consistently moves in one direction, meaning it is either always increasing or always decreasing. A sequence is bounded if there is a strict wall it cannot pass. For an increasing sequence, this wall is an upper bound. Finally, convergent means the numbers in the sequence get infinitely close to one specific target number, which we call the limit. This brings us to the formal statement of the monotone convergence theorem. It states that every bounded monotone sequence is convergent. Conceptually, if a list of numbers only grows larger but is trapped below a maximum value, it is guaranteed to hit a final target value. The formula on screen defines this target value, called L. L is the supremum, which means the least upper bound, or the lowest possible ceiling we can place over the sequence. The symbol S sub n represents the terms of our sequence, and the capital N represents the set of natural numbers. If the sequence values increase, they will eventually squeeze right up against this supremum L. Before we look at an example, let us visualize what this theorem is telling us. On your screen, you see a graph with the sequence index n on the horizontal axis and the sequence value S sub n on the vertical axis. Notice the blue dots. As we move to the right, each dot is higher than the last, showing that the sequence is monotone increasing. But look at the dashed line at the top, labeled supremum L. This is our upper bound. The dots curve upwards and get incredibly close to this dashed line, but they never cross it. The sequence is forced to level off and converge. Now that we have visualized the concept, let us see this with a concrete example. Consider the sequence defined by the formula S sub n equals 1 minus 1 over n. Let us look at the first few terms to get a feel for it. When n is 1, the value is 0. When n is 2, the value is 0.5, then 0.666 and so on. To use our theorem, we must prove two things. First, we need to check if the sequence is monotone. Second, we need to check if it is bounded. Let us prove that the sequence is increasing. We find the next term, S sub n plus 1, by replacing n with n plus 1. Since the denominator n plus 1 is larger than n, the fraction 1 over n plus 1 is smaller than 1 over n. When we multiply an inequality by a negative sign, the direction of the inequality flips. Adding 1 to both sides does not change the direction. Notice that the left side is exactly the formula for our next term and the right side is our current term. This confirms every term is strictly greater than the one before it. We have proven the sequence goes up. Now we must prove it has a ceiling. Because n is a positive integer, the fraction 1 over n is always a positive number. If you start with 1 and subtract a positive number, the result must be strictly less than 1. This proves that 1 is an upper bound for our sequence. Since the sequence is both monotone increasing and bounded above, the monotone convergence theorem guarantees that it must converge. As n gets infinitely large, the fraction shrinks to 0, meaning the sequence converges exactly to its supremum, which is 1. Let us look at a slightly more complex problem. Here we have a sequence defined recursively. The first term, s sub 1, is 1. Every following term is the square root of 2 plus the previous term. If we calculate the second term, we get the square root of 3, which is about 1.732. Clearly, the second term is greater than the first. We suspect the sequence is increasing, but because it is recursive, we cannot just plug in a large number. We will use mathematical induction to prove it is increasing and bounded. We will start our induction by assuming the sequence went up at some arbitrary step k. This means s sub k is less than s sub k plus 1. Now, we add 2 to both sides. The inequality remains perfectly true. Next, we take the square root of both sides. Because the square root function is strictly increasing, it preserves the inequality. Now, the expressions on both sides look exactly like our recursive definition. We have successfully built the next terms, proving that s sub k plus 1 is less than s sub k plus 2. The sequence is always increasing. Now, we must prove the sequence is bounded above. Based on our first term being 1, we will guess that 2 might be a ceiling. We assume for our induction hypothesis that at some step k, the term is less than 2. We add 2 to both sides, giving us 4 on the right. Taking the square root of both sides gives us the formula for the next term on the left and the square root of 4, which is 2, on the right. We have proven that if one term is below 2, the next term is also below 2. Because we have proven the sequence is both increasing and bounded above, the monotone convergence theorem guarantees that a limit exists. We will call this unknown limit L. To find its exact value, we take the limit as n goes to infinity of both sides of our original recursive formula. As n goes to infinity, both the current term and the next term approach the exact same limit L. We can substitute L into the equation wherever we see a limit. To solve this, we square both sides to remove the square root, giving us L squared equals 2 plus L. We rearrange the terms to form a standard quadratic equation by subtracting L and 2 from both sides. Setting a quadratic to 0 is the standard way to find its roots. We factor the equation into two binomials, L minus 2 and L plus 1. This gives us two possible mathematical solutions, L equals 2 or L equals negative 1. However, our sequence started at positive 1 and was strictly increasing. It is physically impossible for it to converge to a negative number. Therefore, we reject negative 1. The sequence converges exactly to 2. So, we have successfully used the theorem to solve problems. Now that we have used this formula, let us understand where it comes from and prove it. We start by letting Sn be an increasing sequence that is bounded above by some number m. Because it is bounded above, a fundamental rule called the completeness property guarantees it has a supremum, which we will call L. We want to prove that the sequence actually converges to this exact number L. To do this, we pick a tiny positive number called epsilon to represent our allowed error. Let us see what happens when we subtract this tiny error. Since epsilon is positive, L minus epsilon gives us a number strictly smaller than L. Because L is the absolute lowest possible ceiling, this new smaller number cannot be a ceiling anymore. It is simply too low to trap all the numbers. Therefore, at some specific step n, the sequence must climb above this false ceiling. And because we already established the sequence is always increasing, every single term that comes after step n must also remain strictly greater than L minus epsilon. At the same time, every term in our sequence is permanently trapped below L because L is the absolute upper bound. And naturally, L is strictly smaller than L plus epsilon. When we combine these facts, we see that our sequence values are squeezed tightly between L minus epsilon and L plus epsilon. This means the distance between our sequence terms and our target limit L is strictly less than our tiny error epsilon. This absolute value formula is the exact formal mathematical definition of a limit. We have successfully proven that the sequence converges to its supremum. We have covered a lot of ground today. Let us review the key takeaways. First, a monotone sequence is one that moves in only one direction, step by step. Second, if such a sequence is bounded, it is trapped and cannot grow to infinity. Finally, the monotone convergence theorem guarantees that these sequences will always settle down and converge to a limit. This theorem is a crucial mathematical safety net, ensuring that approximation algorithms in engineering and physics will eventually find a true final answer. Great job following along.